Hello class, this is Jaime Lopez Rocha and I will be talking about mold design for forming and injection molding. To start off, I'm gonna give a brief outline of what injection molding is, a history of injection molding, the powder injection molding process, mold design, why choose injection molding, and economic factors and importance of injection molding. So what is injection molding? Injection molding is where a powder metal or a thermoplastic is heated and then carefully injected into a mold's cavity. As you can see to the right, this is a very simplified version of what injection molding really is. You can see a metal is often mixed with a lubricant or a binder. This helps increase the green part strength, the green part being the component that is finalized at the end of your injection mold. This isn't the completely final product, as it still has to go through binder removal and sintering. I will cover that more in detail in the following slides. So injection molding is an alternative process for casting, forging, machining. It can be a cost-effective option when mass producing products. Some of your typical products that are made are connecting rods, piston rings, a lot of automotive components, as well as toy plastics, plastics for electronics, and a plethora of things. So going back to the figure to the right, you can see a metal powder being blended with a binder to create what is called feedstock. The feedstock is fed into a hopper, which feeds it into a screw-like mechanism and then injected into a mold. Once that mold has cooled down, which is its cycle time, it is removed and then will go through what we call binder removal process and sintering. This helps to remove the added binder from the final product. This is a brief history of injection molding. It was first used in Egypt around 3000 BC for the production of iron tools. The first modern use of injection molding was to create the tungsten filaments in these light bulbs, as you see to the right. Injection molding expanded rapidly during World War II because of its ability to mass produce products. The first screw injection machine was created by James Worthy in 1946. This greatly improved product quality and is what the majority of today's machines use. So powder metal injection processing consists of a number of steps. First, the powder production. This is where you select the correct powder metal. You have to make sure it is the correct size that you want. This is a big factor in the density of your product, the flow characteristics of the fluid that is injected into the mold cavities, and the compressibility of it. It is blended with what we talked about earlier, a binder and lubricants of sorts to help improve these flow characteristics. And then it is compacted using a clamping force, and we'll cover that in a later slide. Once the green part is completed, it is removed and then sintered, where it is heated up to remove some of the binder material, and then it'll go through finishing operations. The reason they call this component the green part at the end of the actual injection mold is because it's not quite finalized. It is still not at the strength and at the final strength that it should be. Some common materials that are used for powder injection molding are iron and steel. Obviously, you can see that those were the biggest powder metal shipments of 2017 and 2018, followed by aluminum and copper. So now to dive into the powder metal injection mold design. Some of the topics I'll be covering are wall thickness, shrinkage, radii, draft angles, gate location, surface finish, and clamping force. So what does a mold actually consist of? A mold at the end of the screw machine goes through a nozzle. Here's a quick snippet of what a mold actually consists of. As you can see, the powder metal goes through a nozzle, which is fed into a sprue, and that sprue allows the metal to go to these runners. Those runners feed the powder metal into these gates that allow the powder metal to fill the actual parts. Once a part is complete, these injector pins, the mold will open up, and these injector pins will push out the part, and that will be your green part. Wall thickness design is critical for the strength of a component that you're creating. We want to try to maintain a uniform wall thickness at all time. We want to avoid drastic thickness changes and design tapered transition in thickness. You can see that a sharp transition is terrible because the powder metal will not reach the top right corner of that shape. A gradual transition is preferred, but best of all, the tapered transition is probably the best option when designing wall thickness or transitions between walls. We want to absolutely avoid sharp corners, and we want to try to implement a radius in our corners. This will help increase the part strength, and any increase in thickness will increase cooling time. Whenever we're designing our walls, we want to make sure to implement between a 1/4 to 2 degree draft angle, which we'll cover later on, and we want to have a minimum wall thickness of 0.025 inches. Shrinkage often happens whenever a green part is centered. We want to help avoid shrinkage by improving our design. We try to keep as many voids out of our designs as possible. For close tolerance components, prototype units should be made to accurately identify shrink rates. And there's a lot of factors that really play into effect of what causes shrinkage. A lot of it can be flow direction, packing pressure, the incorrect fill rate, rapid cool rates, and again, wall design. Here's a quick example of what a shrink rate density change looks like. We take a coarse copper powder and compact it using a pressure of 275 megapascals. During sintering, the green part shrinks an additional 8%, and we try to find the final density. Using a table from the book, we see that the copper density for that copper powder is 7.6 grams per centimeter cubed. This volume is reduced to 92% of its initial volume, so we just use the equation shown below and find the final density of our component. Mold radii. Adding radii to the inside of corners is needed for optimum part strength, and we want to avoid sharp corners as stated during the wall thickness design. We want to try to implement a 50% radii of the wall thickness for the inner radius and a 150% radii for the outer thickness. What I mean by that is we take the wall thickness, multiply it by 50%, and use that as a guide for our inner radius. We take that same wall thickness, multiply it by 150%, and use that as our outer radii. For example, if we take a 5 centimeter wall thickness, we should have a 2.5 centimeter inner radius corner and an outside radius of 7.5. Draft angles. For draft angles, we should try to target a 1 degree per side to help enhance the release of our green part from our molds. 1 degree draft angles are sometimes rejected by designers, due in part for fit requirements with mating components. In those cases, we try to target a 1/4 to a 1/2 degree draft angle per side. As you can see in these figures here, the draft angles are shown to the right in the correct manner versus parts with 0 draft. Having no draft in our components increases the difficulty of removing that piece from our molds. So having these draft angles really allows for a smooth part release from our mold. Gate locations, we will try to implement a single gate over multiple gates. This helps improve the flow capabilities of our powder metal when it's being injected into these molds. Multiple gates often result in more weld lines and potential gas traps. They do increase mold complexity and often are difficult, or often make it difficult to balance the flow. And as you can see in this figure, the gates are pointed by red arrows. And this is where the powder metal is entering the actual cavity where the part is going to be created. It is important when designing a mold cavity or a mold core and cavity to keep the gates away from stress locations. This will help keep the strength integrity of the components that we're creating and make sure that we don't see any reduced strength in high stress areas of our parts. Surface finishes. Surface finishes are often required for our green components to make sure that they have the required finish that we want. Many powder metal injected components are subject to finishing operations like machining to be able to get specific geometric features that we want. Grinding to help improve our dimensional accuracy and surface finish. We also see plating to help improve any resistance to corrosion and wear. And heat treating. This also helps increase the strength and hardness of our green components. Our green part. Here are some examples of the surface finish to mold samples. As you can see, the picture to the left shows a more grainy look-like figure, while the figures to the right show a little bit more polished, more refined surface finishes. Clamping force. Clamping force is often a value that we have to calculate to see what the capabilities are of our machine and to see if it meets the requirements of the parts we're trying to create. The clamping force is the force required needed to mold the metal, and it is found by multiplying the pressure inside the cavity by the total projection area and the number of cavities within the mold. For example, if we have an 8-piece mold and we're trying to mold a copper slab that it measures 5 inches by 5 inches using a machine of 2 tons per square inch, we can find the clamping force by multiplying the 2,000 psi from the machine by the 25 inches squared of the surface area of the copper slab that we're creating and the number of cavities within the specific mold that we're using. In this case, the clamping force for our 8-piece copper our 8-piece copper slabs would be 200-ton needed clamping force. So why choose injection molding? Injection molding allows us to create complex shapes with wall thicknesses as small as 5 millimeters. The higher the complexity of the shapes that we're trying to create, the higher the cost. Some of the mechanical properties are nearly the same as raw products. We can maintain good dimensional tolerances and we can also create high production rates with these multi-cavity type molds. One of the biggest limitations for injection molding is the high cost for small production runs and the need for fine metal powders. So it's very difficult to prototype using powder metal injection molding. As stated before, there's some economic benefits to choosing powder metal injection molding. Some parts can be produced at net or near net shape, meaning the green part that comes out of the injection mold is almost nearly the final product that we need or that we're trying to obtain. There's an increased competitive factor. Injection molding has become increasingly competitive against casting, forging, and machining. Although one drawback is the more complex the parts that we're trying to create, the mold complexity increases, and therefore the increased cost to manufacture or produce those specific components also increases. Here's a quick table from our textbook showing the weight comparisons for aircraft components produced by forging and powder metal injection processing. As you can see, the cost savings is pretty significant for some of these components, substantially up at least 20% to up to 50%. So it's definitely an option, a cost-effective option when mass producing certain components. Thank you, class, for tuning in to my powder injection molding design PowerPoint. Here are a few questions to go along with the PowerPoint presentation, which will also be attached as a Word document. Thanks.